So let us look at the first result of this section. Here we are given two non-zero polynomials fx and gx over the field f, that is two non-zero elements in this polynomial ring. Then we have to prove that the degree of their product is equal to the product of their degrees. So let us start the proof by considering two polynomials, that is considering expressions for them. Let fx be a naught plus a1x plus etc. am x to the power m and gx be b naught plus b1x etc. plus bn x to the power n, where m and n are non-negative integers and am is non-zero and bn is also non-zero. See, we will get non-zero coefficients because the polynomials are given to be non-zero. So we cannot have all the coefficients of f to be 0. Similarly, all the coefficients of g cannot be 0. So we will get non-zero coefficients, and m and n are the highest levels for which the corresponding coefficients are non-zero. So they will determine the degrees of these polynomials. So you can see that degree of fx is m and degree of gx is n. Okay, now we are interested in showing that the degree of fx gx is m plus n. So let us naturally, that means we would try to calculate the coefficient of x to the power m plus n. To make it look somewhat neat, we consider this also. Let the polynomial fx gx, the product, be this: c naught plus c1x plus c2x square etc. We know it will end at some stage, but we are not showing that here, where ci belongs to f for all non-negative integer I. Note that okay, now what is Cm plus n? Let us try to figure this out. Cm plus n, we know from our formula, is a sum like this: aibj. The condition on I and j is that their sum should be equal to this label, this suffix. Okay, now looking at these expressions for f and g, what do we see here? I can take the value m. In that case, we would be taking am in place of ai, and j can take the value n. So we would be taking bn in place of bj. But what about other terms? Do other terms occur or not? Let's see. If I is, say, less than n, say I is less than m, then what happens if we add j on both sides? Then we get I plus j is less than m plus j, but you know that I plus j is m plus n. Now you can cancel m from both sides of this inequality to obtain this. That is, if I is less than m, then to keep the sum m plus n, j has to be greater than n. But if j is greater than n, then the bj's with higher values of j are all 0. So if I is less than m, then because j exceeds n, that term will be 0, because that bj is 0. So I cannot be less than m. I has to be greater than or equal to m. But if I is greater than m, then you can see from here, from the expression for fx, that ai then is 0. So the only term that is there, I mean that we know that it's not, I mean I should not say not 0, but the other terms in this sum are definitely 0. So we are in this sum, actually we are left with only one term, and that is the one which we get for the choice I equal to m and j equal to n. Because I has to be equal to m, in that case if I is m, j has to be equal to n. So a m b n. We are now going to write this systematically. Note that this is equal to, in fact we are just going to write everything we described just now. aibj, where I plus j is equal to m plus n. If I is less than m, then j is greater than n, and so bj is equal to 0. If I is greater than m, on the other hand, then ai is equal to 0. So Cm plus n is equal to bj am bn. Now you use the fact that am and bn are non-zero, so their product will be non-zero, because these are elements in the field f, and every field is an integral domain. It has no non-zero zero divisor, so that's why this is not equal to 0. Okay. Now what happens if this suffix of c is even greater than m plus n? We have to check that also. If say, okay, we are already taking I and j, no? So let us take ck. If k is an integer satisfying, or instead of starting the sentence with if, let's write like this: let k be an integer satisfying this k is greater than m plus n. Now in the expression for ck we will again have a sum like this. Now I plus j is equal to k. Okay. If I comma j are non-negative integers such that I plus j is equal to k, then I plus j has to be greater than m plus n naturally, because k is greater than m plus n. So either I is greater than m or j is greater than n. What is the negation of this disjunction? This is a disjunction, no? This is or, a statement which is one statement or another statement. The negation of a disjunction is the negation of this and the negation of this. That is, if this is the disjunction P or Q, where P and Q are two statements, then their negation is equivalent to, you already know this law from logic, negation of P and negation of Q. It becomes a conjunction. So that means if this is not the case, then I is less than or equal to m and j is less than or equal to n. But then if this is true, then I plus j would be less than or equal to m plus n, which will contradict the situation, contradict the present inequality. So that's why either I has to be greater than m or j has to be greater than n. But then either if I is greater than m, then ai is 0. Either ai is 0, or if j is greater than n, bj is 0. So ck which is this sum, it has only terms where at least one of the factors is 0. So this is equal to 0. So that means whatever this polynomial fx gx ultimately turns out to be, we know two things for sure. One is that the coefficient of x to the power m plus n, which is cm plus n, is non-zero, and all the coefficients that come after that, that is the c case where k is greater than m plus n, they are all 0. So this polynomial fx gx has degree m plus n, because the coefficient of the corresponding coefficient cm plus n is ambn, which is non-zero. Okay, so we are now going to write this, but I think I already need ink. This implies degree of fx times gx is equal to m plus n, which is degree of fx plus degree of gx. So that's what we wanted to prove, and this result is very important. It immediately tells us quite a few things. One of them is this corollary. This corollary again has no number. If fx and gx are two non-zero elements in the polynomial ring fx, then degree of fx is less than or equal to degree of fx gx. Do you see that this is one of the things that we know that we need in order to be able to say that fx is a Euclidean ring, namely that the d value of a is less than or equal to the d value of ab, where a and b are two non-zero elements in a Euclidean ring. So we need this result, and it will now come as a consequence of this, of the previous result. Proof. By the previous lemma, we have degree of fx times gx is equal to this. Now note that degree of a polynomial, the way we have defined it, it's always a non-negative integer. It's either 0 or a positive integer. Since so that means this is greater than or equal to 0. So we have is greater than or equal to this. So this tells us that if we multiply a polynomial by a non-zero polynomial by another non-zero polynomial, then the degree either stays the same or it increases. Degree is somewhat like entropy from physics. It either stays the same or it increases. I am saying this in a vague manner, okay? Now there is another corollary. So far we have known, or we have the fact that fx is a commutative ring with unit element, but in fact it's more. Fx is an integral domain. to say that fx is a Euclidean ring, it first of all has to be an integral domain, because by definition every Euclidean ring is an integral domain. So this is the corollary that states that is an integral domain So since already fx is commutative, the only thing we need to show is that it has no zero divisor. Let fx and gx be two non-zero polynomials in fx. By lemma 391, the degree of their product is the sum of the individual degrees. So this sum is greater than or equal to 0. So that means fx gx cannot be the zero polynomial. In fact, it cannot be zero polynomial, and that's why we are able to find degree. So actually there is nothing to write here. The proof of this corollary is contained in the proof of that lemma, where namely we proved that the coefficient of this x to the power m plus n turns out to be ambn. So there itself you can see that the product fx gx has a non-zero coefficient. So that itself tells us that the polynomial is non-zero, and that's why there is no zero divisor. Or in fact we can, instead of writing this, we can proceed like this. We have already seen in the proof of lemma 391 that the coefficient of x to the power m plus n in fx gx is the non-zero filled element ambn, where am comma bn are the coefficients of x to the power m comma x to the power n respectively, and m is the degree of f and n is the degree of g. Hence, fx gx is not equal to 0. This shows that this is an integral domain. So it's a corollary to the proof of lemma 391 rather than the lemma itself. Okay, so we have got the fact that fx is an integral domain. We have also got this inequality. So what is left for us? The thing that is left for us to show is that the Euclidean algorithm is true. Namely, you can divide a polynomial by a non-zero polynomial to get a quotient and a remainder which satisfy so and so properties. But before that, let us just note one more thing. Since fx is an integral domain, what is that result? Theorem 361. Allows us to construct its field of quotients. Recall that every integral domain, we have already seen this, every integral domain can be embedded in a field which is the field of quotients of that integral domain. In fact, that's how the integral domain of integers is embedded in its field of quotients, which is the field of rational numbers. This one also can be embedded in its field of quotients, and that field has a name. This field is called the field of rational functions in X over F. So we need to take only one more step towards proving that fx is an integral domain, and that step is this next result, lemma 392. Oh, they are calling it the division algorithm. Anyway, it doesn't matter what we call it as long as the result stays the same. Given two polynomials fx and gx in this polynomial ring where say gx is not the zero polynomial. There exist polynomials qx and rx in fx such that fx is equal to qx times gx plus rx, where either rx is equal to the zero polynomial, or if it is a non-zero polynomial, then its degree is strictly less than the degree of gx. So that is the division algorithm, where we take the view that we are dividing fx by the non-zero polynomial gx. Qx is a quotient polynomial and Rx is a remainder polynomial. Since our objects are polynomials, so everything that we get is a polynomial. It can be a constant polynomial, thus giving you a field element, but after all it's a polynomial. Okay, so now we look at the proof, and the proof is by induction on the degree of fx. But to be able to apply induction, we have to take care of a special case separately, namely the one where fx is 0, because in that case it has no degree. If fx is equal to 0, then fx can be written like this: 0 times gx plus fx. So fx itself takes the role of a remainder, because the remainder is allowed to be 0. So in this case fx is 0. So in this case the result is true. So we now assume fx to be a non-zero polynomial, so that it has some degree. It may be 0, in which case fx is a constant, but it may be more. We now apply induction on degree of fx. Okay, so what is the smallest possible value of this? 0, when f is a constant polynomial. If degree of fx is equal to 0, then there are two cases. Now comes the question of looking at, under this condition, gx itself may or may not have degree 0. Then there are two cases. If degree of gx is not equal to 0, then fx can be written like this, 0 times, but we cannot write. Okay, so what is happening here, I cannot take, even if if degree of gx is not equal to, okay, yes, yeah, what I was going to write is correct, plus fx, where now we don't have fx equal to 0, but its degree is greater, less than the degree of gx, where degree of fx is equal to 0, which is strictly less than the degree of gx. Note that this condition that gx has non-zero degree only means that gx has positive degree, because degree cannot be negative, but fx has 0 degree, so this inequality is true. So in this case, fx plays the role of the remainder. If, however, degree of gx is equal to 0, then gx is a constant polynomial C belonging to f, say. In this case, fx can be written like this, fx times C inverse gx plus 0, because gx is equal to C, and since it's given that gx is non-zero, so that means C is a non-zero field element, so its inverse exists, and the inverse, if you multiply that with gx, it will give you 1. So we will have fx back, plus you can write 0. So in this case, we have again expressed fx as a polynomial in capital Fx times gx plus something, a remainder, where the remainder is 0. So we have seen both the cases. In both the cases, our assertion is true, and this is the basis for our induction. This is the basis for our induction. Now let n be any positive integer, and we are now going to make the induction hypothesis, and we assume that our result is true for all polynomials of degree, all polynomials means all non-zero polynomials of degree less than n. The moment we mention degree, that means non-zeroness is assumed. Okay. Now we consider a polynomial fx which has degree equal to n. Let degree of fx be equal to n. Here also two cases occur. If degree of fx is less than degree of gx, maybe in spite of having the degree of fx equal to n, gx still may be a polynomial of higher degree. That is entirely possible. Then fx is equal to 0 times gx plus fx, where degree of fx is less than degree of gx. So if this inequality is true, then we are again in a position to consider fx itself as the remainder, and our job is done. And now finally we come to the case where degree of fx is greater than or equal to the degree of gx. Now assume degree of fx is greater than or equal to degree of gx. In fact, let us be more specific and consider the expressions for these polynomials. Let fx be equal to a0 plus a1x plus etc. am x to the power m, and gx is b0 plus b1x bn x to the power n, where m and n are non-negative integers and am and bn are non-zero. So degree of fx is m and degree of gx is n, and according to our assumption, m is now greater than or equal to n. Okay. Now define, before defining anything, I need some ink. Now, in order to be able to use the induction hypothesis, we want a polynomial whose degree is less than n, and we will achieve this by actually defining one such polynomial. Define f1 of x to be, we want to reduce the okay, so what, hold on, I think I have taken it wrongly. Degree of fx is n, so this should be taken as n, and this should be taken as m, a n b m. Okay, sorry about that. So we want to do what? We want to reduce the degree of fx from n to something smaller. That means we want to get rid of this term. So what we will do, we are going to take the help of g in creating such a polynomial. Using f and g we are going to achieve that. For that we are going to subtract from fx this thing, an divided by bm times x to the power n minus m gx. What will this do? What this does to the entirety of gx is not our concern. What it does to the last term of gx is what we are interested in. Let us see what happens when we multiply this one, this polynomial and the last term of gx. Note one more thing, that since bm is non-zero, so this quotient an divided by bm is actually an element in the field. So this thing is a polynomial. Plus we have also taken n minus m, which is permitted because n is greater than or equal to m. So this expression is a polynomial in fx, and as such this linear combination is a, I should not say linear combination, but this combination, this expression, this f1 is a polynomial in fx. In fact, we can first mention that and then we will see what properties f1x has. Note that since bm is not equal to 0 and n is greater than or equal to m, f1x is a polynomial in fx. Okay, now comes the question of what we get if we multiply this with this term. bm, they cancel each other, and we have minus an times x to the power n minus m times x to the power m, that is minus an times x to the power n plus an times x to the power n that we have here. They cancel, okay, and the resulting polynomial f1x, whatever it may be, it does not have the term where we have x to the power n. It has terms with smaller degree. Okay, what term, what is the degree of f1 of x? We are not interested in that. Whatever f1x is, it has smaller degree than n, or it is equal to 0. Now here also again two cases come. If f1x is equal to 0, then this one is 0 means what? fx is equal to an divided by bm times x to the power n minus m times gx plus 0. So our assertion is true with this as quotient and 0 remainder. If f1x is not equal to 0, then one can see that its degree is strictly less than n, like how we have seen right now. So by the induction hypothesis, there exist polynomials what shall we, let us take something, say tx and rx belonging to fx such that f1x is equal to tx times gx plus rx, and where either rx is 0 or its degree is less than the degree of gx. So here we have applied the induction hypothesis on the polynomial f1x. The divisor gx stays the same, it's there. Hence, now if you look at the expression for f1x, you see that it is fx minus a multiple of gx. This thing we can take on that side and combine it with this term involving gx, having gx. Hence we have, doing that we get fx equal to an divided by bm times x to the power n minus m plus tx times gx plus rx where either rx is equal to 0 or its degree is less than the degree of the divisor polynomial gx. So this completes the, because again we have got the form we want for fx. This completes the induction. And hence the proof. So we now have the one missing piece that we needed for fx, so that we can call it a Euclidean ring, and we just simply are now going to state that fx is a Euclidean ring, because we have all the pieces needed for this statement available to us. So this is theorem 391. fx is a Euclidean ring. And the proof you can understand. What are the things we need? First of all, fx needs to be an integral domain. It is. We have already seen that. Then there should be a function defined on the non-zero elements of fx that takes on non-negative integral values, that is our degree function, which satisfies this property first. For two non-zero elements fx and gx in the polynomial ring. This one we have seen as a corollary to the first result that we proved today, lemma 391, and the second one is the division algorithm, which is also true. So all of these things tell us that fx is a Euclidean ring. Now if you go back to the section on Euclidean rings, there we proved many things, right? That a general Euclidean ring has all the properties, like for example, every Euclidean ring has a unit element. In this case, that however is trivial because we already know that fx has a unit element, namely the constant polynomial 1, where 1 is the unit element in the field. But there are other non-trivial results also. The main result in the theory of Euclidean rings is that every Euclidean ring is a principal ideal ring. Every ideal is generated by a single element. So that same thing continues to be true in fx, and the other things that come along with that as consequences of that fact, they will also be true, or I mean their proper version will be found in this particular Euclidean ring. So those things we will state, and we will see their consequences also in the coming video. So I end this video here. If you are new to my channel, please subscribe, consider subscribing if you find these things useful or interesting, or both. So with that, I sign off for today. This is me, Lucifer, from A Mathematical Room. Have a nice night.